That's almost a record. It worked on the second try. Okay, so we're on example 6, and this one is entitled Piecewise Fun. Not Piecewise Function, just Piecewise Fun. It says, determine if the IVT applies to the following function on the following intervals. Explain specifically why or why not. Okay, so the question that y'all had on the last free response on the previous exam was, is the function continuous or not, right? We can kind of now ask that same question by, does the IVT apply? Because if the IVT applies, then we know what about the function? It's continuous on the closed interval. Yeah, so, all right, let's take a look at it. So this is kind of, again, like the free response. We have a big piecewise function here. Pre-cal is just getting acquainted with piecewise functions, and they are not comfortable with them. They don't really like them yet. But y'all are just like, oh, another piecewise function, right? So we're looking on the closed interval from -4 to -2. That's a closed interval. So -4 is the left endpoint, -2 is the right endpoint. So let's see, which pieces are we going to be using? Only the top, right? Only the top, because it's less than or equal to -2. So would that function be continuous from -4 to -2? Yes, because the piece itself is going to be a line. Not a line, our student friend, but a line, our linear friend, right? And we know because the limit from the left of -2 is also going to be the function value at -2, because it's less than or equal to, we know it's going to be continuous at the right endpoint, correct? So, yes, we'll just say yes, f is continuous on the interval from -4 to -2. Boom. That's all we have to say. The only question was really the right endpoint, but it worked. All right. Bless you. What about from -3 to 0? Now which pieces is that going to involve? The top one? We start on the top one, and then we finish on the second one. All right? So we need to check now. Let me go ahead and write it up here where I can see it. -3 and 0. Are we going to have to check our endpoints here? Will it be continuous at the endpoints automatically? Yes, because -3 is on the interior of the top piece, which is a line. So it's continuous at -3. And 0, the right endpoint, is on the interior of x²+1, which is also continuous everywhere on the interval. So we know it's going to be continuous at the endpoints. The only place where it might not be is where? At -2, where it switches. So we can just kind of do a real quick mental check. We're not going to write out all the stuff, but the limit from the left to -2 is also the function value at -2. We already saw that on the first one. And that value is what? 5. The limit from the right to -2 by direct substitution is 5. So the function is continuous at -2. And we know because it goes from polynomial to polynomial on the interior, it's also continuous at -3 and 0. So this is yes. F is continuous on, and we'll just say the interval again, -3 to 0. Oh, that looks like a parenthesis. Yeah, bracket. All right, -1 to 1. Which pieces are we using for that? Very good. Most of the second and just one piece of the third, right? Namely the right endpoint. And so if we're starting at -1, we're starting on the interior of a parabola. So the left endpoint should be good, correct? I need to then move all the way to 1, so I really just need to check the right endpoint. So notice now this one is not less than or equal to, so I have to check. I'm going to go ahead and write it out here just to kind of explain what I'm doing. The limit as x approaches 1 from the left of f by direct substitution is 2, and then f of 1 by direct substitution here is 3. Okay, so we don't have to do the 3-step definition, remember, because it's an endpoint rule. We only have to check those 2. But 3 doesn't equal 2, correct? So is it continuous on this closed interval? No. We'll say f is not continuous. Here's how we'll say it. At x equals 1. And then why is that relevant? We'll put that is in the closed interval from -1 to 1. That's the easiest way to write it. Okay? The function is not continuous at 1, which is on the closed interval, so therefore, no, the IVT does not apply. It's continuous on this interval from -1 to 1, parenthesis, but then that's not IVT, right? IVT requires the closed interval. All right, you do this one on your own from 1 to 4.5. It just comes out like that. It's my finished background, I guess. Good. I know what you mean when you do that, right? Yes or no? I think it is, right. So if we're starting at 1 as a left endpoint, we're actually starting on this piece here, and 3 times the square root of x, that's going to be continuous everywhere to the right of 0. It's continuous over its domain. So I know that that one's continuous on the open interval from 1 to 4 for sure, as it travels along that piece. But I need to check if it's continuous at 4, right, before I can get to 4.5 as I make the exchange. So let's see, I need to check the, now in this case, I need to check the 3-step definition because 4 is not my endpoint, 4.5 is. So the limit from the left of 4 is, square root of 4 is 2, times 3 is 6. The limit from the right of 4 and the function value at 4 are both the same. And that's 6 over 5 minus 4, that's 6 over 1, which is also 6. So it is continuous at 4, all right? And so now all I have to do is get from 4.5, or from 4 to 4.5. Can I travel on this function a half unit past 4 without running into any problems? Yes, because that function, that piece, is only undefined where? At 5, okay, where it has a vertical asymptote. So this one is yes. F is continuous on this closed interval. Okay, so if you write it like that, that's great. That's kind of how I'd expect it on a quiz or a test. But if you know how to do that, and you just want to do this, like Jack did, I know what that means, right? That's good. All right, how about from 2 to 7? No? 2 to 7? If we go from 2 to 7, we're starting on this one, which is on the interior, so we know it's good. We know we're going to get past 4 with no problem, correct? Because we already checked that. It's continuous. We're connected at 4. We just then have to travel on the bottom piece all the way from 4 to 7. Can we get all the way to 7 without any problems? No. This one has a built-in vertical asymptote at 5. So anytime we try to have an interval that spans 5, it's not going to work. So we'll say no, F is not continuous at x equals 5, which is relevant because that's in now the interior, but it's in the closed interval from 2 to 7. All right, so asking if the IVT applies is really just seeing, is the function continuous on a closed interval? So I could ask it either way. Is the function continuous on a closed interval? Does the IVT apply? Really the exact same question. All right, so that's kind of, for lack of a better word, fun. Was that fun? Kind of fun. And notice we did that without any visuals. So if you need to go off to the side and kind of sketch those pieces, that's fine. But we're using the analytical tools that we've developed, the limit, the function value, and then the other side limit. Okay, so we can use the IVT, as we noticed yesterday, to prove the existence of a value. without actually knowing where that value occurred, like that temperature on the back porch. So here's a nice little example. And this kind of looks more like what a free response setup would look like later on. The velocity of a particle moving horizontally along the x-axis. Well, you're going to get tired of particles moving on x and y-axis, okay? So the x-axis is just a track for this particle to move along. Left, right, left, right, left, right. Its velocity is given by the continuous function. The velocity is a continuous function v of t. T is measured in seconds, v is in feet per second. Selected choice hand-picked values of v of t are given in the table below. All right, so notice that the initial velocity at t equals 0 is -3. What does the negative imply? The particle is moving in reverse? Well, we'll learn this later on. Velocity sign tells you which direction it's going, because velocity is the rate of change of position. So if you say the velocity is -3, you could actually say his position is decreasing by 3 feet each second, which basically means he's moving left, okay? And again, a negative would mean he's moving left. Positive means he's moving right. So again, there's a whole section on that later on, particle motion. We'll actually cover it twice, okay? But basically, the sign of velocity, because it's a vector, tells you which way you're going. So for linear motion, positive is always in the positive direction, which is either right or up if we're on a vertical line, and negative is always in the negative direction, which is left or down if we're on a vertical line. Okay, explain why there must be a time value on the interval from 2 to 5. So explain why somewhere in here there has to be a time where the particle is at rest. At rest. What would that mean? What are we trying to prove there? Give ourselves a, are we trying to prove that the particle is sleeping in his bed at some time, or lounging on a recliner watching college football? What does at rest mean? Ah, very good. So give ourselves a numerical target here. So we've translated the problem now to explain why there has to be a time from 2 to 5 where the velocity is 0. Okay, that's what that means. Yeah, let's see. If at t equals 2 seconds, he's traveling to the left at 0.5 feet per second, and at t equals 5 seconds, he's going to the right at 2 feet per second. Why would he necessarily have to be at rest somewhere in between there? Very good. Because 0, the value we're looking for, and remember, I said IVT is also known as the YVT. These values, if we were to graph it, would be on the y-axis. So whenever you're trying to prove a function value that would be graphed on the y-axis, whenever you're trying to prove that, it's the YIDT. Good. So because 0, the y value we're trying to prove, falls between a negative and a positive, and additionally, because our function is what? Continuous by the IVT. Okay, so let's look at this. Where does it say it's continuous? It just says by the continuous function. It doesn't say where. So what does that mean? All across its what? Domain? Yeah. If it says a continuous function, you can assume that it's going to be actually for all real numbers. Okay. If it wants it to be on a smaller interval, it'll specify. So when it says a continuous function, it's continuous everywhere. Okay. All right. So here's what we have to say. We'll say they're telling us that the time, and this is kind of important too. They're telling us that the time where it is 0 velocity is strictly between 2 and 5, which basically means the particle's not at rest at 2 and the particle's not rest at 5. And we know that because it's negative and positive. But for the IVT to apply, we need to say that the function is continuous on what type of interval? Closed interval. So even though they're telling you prove that it exists on this open interval, you have to say that the IVT applies because it's continuous. So here's what you'll say. V of t is continuous on the closed interval from 2 to 5. And now we're going to state the intermediate part of that, which y'all already picked up on. And V, you could say, how about this? V of 2 is less than or equal to 0, which is less than or equal to v of 5. You could do it that way. Okay, so here's the number that we want, the number we're trying to prove. And we show that it's between the other two numbers. Now, you got to be careful. You can't always just say the x value that's smaller is less than the y value, x value that's bigger, because we're comparing y values. But I know that's the case, right? Negative is smaller than positive. Or if you want to actually use the numbers from the table, because the numbers are given, you could say negative 0.5 is less than or equal to 0 is less than or equal to 2. All right, you can even use absolute inequalities there. You don't have to say less than or equal to. You could say less than if you want. But you're basically saying that the number we want falls between the other two. So v of t is continuous on the close, and that, so, comma, by the IVT, and now all you have to do is reuse their words, which would be right in here, starting with there. By the IVT, there must be a time on the interval. You could write the interval like this if you want. T epsilon 2 to 5, where the particle is at rest. So you reuse their words to finish it off. Now, it was important that you define the particle at rest to be v equals 0. Because when you put v equals 0 over there, and then 0 shows up in the middle of your inequality, we know that that's the value you're trying to prove. So that right there is the essence of an IVT proof, okay? Basically, it's continuous on the closed interval. The value, the y value, is in between the two y values on either end, and put them in increasing order, and therefore by the IVT, reuse their words, there exists a value, okay? This typically shows up when the argument's like this on a free response, and it's worth at least 2 checks. Okay, sometimes it's worth 3 checks. IVT is the YVT. Now, again, does that help us determine exactly where between 2 and 5 it was at 0? No, it could have actually happened more than once even, right? It could have been 0 many times, but we know for sure there had to be at least one time. Where is anybody's guess? We would need more information in order to determine that. So the IVT, once again, is an existence theorem. It tells you something exists without actually proving or showing where. All right, so let's look at the next one. This is the type of question that you'll have in your worksheet if you've looked at it. Okay, show that there is a positive real solution to the equation x to the 5th equals x plus 2. Show that there is a positive real solution. All right, so there's 2 ways to do this. Number 1, you can find that positive real solution, right? And you can put it in your hand, and then you can just go around showing people, look, there's the solution to that equation. You see that? Seeing is believing, right? Can we do that? Let's try it out. Let's try x equals 1. 1 to the 5th equals 1 plus 2? No. Let's try 2. 32 equals 4. No. How about 1.465? Let's try that. Ooh, I can't raise that to the 5th power. I can't do that. So anyway, it just says to show that there's 1. It doesn't say to find it, right? That's one way. You could actually find it. You could prove something by finding it and showing people. But short of that, how can we prove that there's a solution without finding it? IVT. Now, because we have variables on both sides, we're going to reframe the question in a way that's more helpful, okay? So what I'm going to do is I'm going to take everything on the right side and bring it across to the left side. And now I'm setting it equal to 0. So reframing the question now, showing that the top one has a solution is the same as showing that x to the 5th minus x minus 2 has a 0, has a root, okay? And if you even want to name that function f of x, you could do it like that, all right? So now I'm just trying to prove that f of x equals 0. F of x is another name for y. We're trying to prove a y value, y IVT, right? So here we go. Is this function that we've now defined, is it continuous? It's a polynomial. It's continuous everywhere. So I need to have some numbers. I need to have a closed interval. How am I going to do that? I'm looking for a positive real solution. Any ideas? Is 0 positive? 0 but not included? So if I'm going to use 0, remember I'm going to have to show that it's in somewhere between 0. Oh, yeah, there you go. 0 but not included. So what do I get if I plug in a 0? Let's try that. I get a -2, right? Now, I don't want to plug in any negative numbers, do I? Because I'm looking for a positive real solution. 0 would be the very least I could plug in, and it's not a solution. So now I just need to pick a positive number and plug it in and hope that it's what? If I plugged in a 0 and got a -2, and I'm trying to show that there is a 0, then I need to pick an x value that when I plug it in gives me what type of number? A positive number. There you go. Would 1 do the trick? No, but I could use 1 as my lower bound, right? 1 minus 1 is 0, so that's also -2, right? So let's try f of 2. Let's just keep it easy. That's 32 minus 2 minus 2. That's going to be 28. Is that good enough? Yeah, so here's what I know. I'm welcome to use 0. I know somewhere between 0 and 2, the sign changed from negative to positive. And that might not be bad. But if I use 1, what does that do to my interval? It shrinks it down, right? So that might actually be more desirable. Not only knowing it exists, but if you can narrow down that interval where it lives, it might be better. So there's nothing wrong with using 0. But I'm going to use 1. So here's what I'm going to say. Now that I showed my calculations, I'm going to say since f of x is continuous. Now you could say continuous for all real numbers because it is, and that'll include any closed interval in the whole wide world. But when you're using the IVT, you want to speak specifically to the theorem. So because I'm going to use x equals 1 and 2, I'm going to say since f of x is continuous on, and I'm going to do the closed interval from 1 to 2, comma, and since, and just like with the limits, we can use the numbers. You can either say, let's see, f of 1 is less than or equal to 0 is less than or equal to f of 2. You could do that. Or you could use the actual numbers. -2 is less than or equal to 0, which is less than or equal to 28. So either one of those because you have it labeled up above. Okay, then comma by the IVT. And believe it or not, the IVT is okay to abbreviate even on test day, on the day of the AP exam. You can abbreviate intermediate value theorem, IVT. By the IVT, comma, now we'll restate the question. X to the 5th equals x plus 2 has, and what did it say, at least 1? Has a positive real solution. And you can even add something here. You could say between x equals 1 and x equals 2. That last part is not really needed, but it is kind of nice. It's nice to include it. All right, so if we had time, what I would do is go to my calculator. I would graph that in y1, I would graph that in y2, and we would find the point of intersection, and you would actually see what it is. Maybe I'll do that while y'all are at lunch, because I got to load my calculator, and doing it on the iPad now is a little bit tricky. So anyway, there's the IVT. Yeah. Mm-hmm. There's nothing wrong with saying that. You could say strictly less than if you want. Yeah. That would actually make the interval smaller. So if you wanted to do that, that's fine. Yeah. Because I know the endpoints are not 0, I can certainly do that as well. Yeah. There's nothing wrong with saying less than or equal to. You're just making the interval a little bit bigger. It would be like the same thing down here of using 0. I know there's a solution between 0 and 2. Well, certainly if there's one between 1 and 2, there would be one between 0 and 2. So, yeah, good point. Maybe it's actually better to say less than, because we're making it a little bit smaller again. Okay, so cool. We'll go to lunch, and then afterwards we'll kind of find what that solution is, and then we'll jump into example 9. So have a great lunch. Don't eat too much or too fast. Chew, chew, chew like a train.